So folks, a good question to ask after we've explored exact ODEs and we've learned the test to determine if an ODE is an exact, and after you've had some practice with finding that psi of xy that we're trying to find to solve the exact ODE, you might be asking, okay, so suppose we know this ODE is exact and we find the particular psi of xy that satisfies, well, if we take the partial derivative of psi with respect to x, we get m, and if we take the partial derivative of psi with respect to y, we get n. Then how can we call psi of xy plus c equals 0? How can we call that our solution? Why is that? To understand this, I think you need to know a little bit about the multivariable chain rule for calculus. So if you haven't had Calc 3, you may not have seen this. So what I'm about to do may not make sense. So you might want to postpone this discussion until after you've had Calc 3. But I'll just show you that we think of this psi of xy, it's a multivariable function. And so it has two different inputs, x and y. And what I'm setting up here are the tree diagrams that we do with the chain rule in multivariable calculus. But the key is remember that x is an independent variable of the function y, and so I'm going to add this leg to the chain here. So if I were to talk about taking the derivative of the function psi, I'm going to take the ordinary derivative of psi with respect to x. And it's the ordinary derivative because even though psi is a function of x and y is a function of x. So I really just have one independent variable here. So taking psi dx gives me, by the multivariable chain rule, partial psi partial x plus partial psi partial y times derivative of y with respect to x. So just as a reminder, if you have seen this before, for every leg, if there are two branches come from it, I use the partial. So that's why when I wrote out this branch, I used partial psi partial x. That's for this here, because it was in tandem with this branch. And I'm looking at all the ways I can trace back to the variable x. That's how we use these tree diagrams. And so when I take partial psi partial y, again, that's in tandem with this branch, so that's why it's partial. But notice that y depends on only one variable, x. So for this leg of the tree diagram, I just use the ordinary derivative. Folks, if you don't know these tree diagrams, please don't stress about them. Instead, just know this is how we take the derivative of this function psi with respect to the variable x by this expression here. The next thing I'm going to do is I'm going to, and we've seen this a few times over our calculus careers, I'm going to multiply both sides of this expression by differential x. And so doing so gives me differential y is equal to, and I'd like to rewrite this as psi of x, differential x, plus, and then here we'd have psi of y for this expression here, dy dx times that differential x. And in one sense, we could think of those as canceling. And so I end up with the differential y is equal to psi of x dx plus psi of y dy. But remember, we chose our psi to satisfy these two requirements. Psi of x is m and psi of y is n. And so really this is differential psi is equal to m dx plus n dy. And from our original differential equation, we know that this whole expression is equal to 0. To satisfy the differential equation, we're looking for m, and we're looking for something so that we satisfy that this whole expression equals 0. And so hopefully that shows why, if I'm thinking about a function that would satisfy this expression, we want its derivative to equal 0, so that would be why this psi of xy needs to equal some arbitrary constant. I'm thinking of a function whose derivative is 0, so that's why we say psi equals a constant is our solution, or put another way, psi of xy minus that constant needs to equal 0, or just because it's that arbitrary constant, sometimes you'll see it written this way with a plus c, needs to equal 0. So hopefully you see why we're looking for a psi that satisfies The partial derivative of x of it equals m, partial derivative of it with respect to y equals n, and that will then satisfy this equation right here. And the reason why it satisfies that equation is because of this multivariable chain rule. And because we satisfy that multivariable chain rule, that's why we would claim that psi sub xy plus c equals 0. That's why we state that that's our solution. Folks, I hope this helped clarify. If not, please let me know. Otherwise, I'll see you in another video. Thanks.